This is Bridge 157 in LaPorte County, Indiana, and it's about to endure its first winter. Here in northern Indiana, that means that it will be exposed to cold temperatures well below freezing, it will be blanketed in ice, and it will be doused in harsh chemical deicers such as calcium chloride. Any crack in the surface of this bridge offers those deicers a chance to seep in and corrode the steel reinforcement, or for water to leak in and freeze, increasing the size and severity of the crack. However, Bridge 157 has a significant advantage going into the winter. It was internally cured.
So, what exactly is internal curing, and how do we make it? The American Concrete Institute defines internal curing as a process by which the hydration of cement continues because of the availability of internal water that is not part of the mixing water. In this illustration, we see a curing comparison of plain concrete to internally cured concrete. You can see the plain concrete is completely dependent on surface curing, which only penetrates the concrete surface by a few millimeters, whereas the concrete with the pre-wetted, expanded shale, clay, or slate lightweight aggregate provides water internally, which is distributed throughout the concrete matrix. Internal curing water is hidden within the lightweight aggregate and begins to release at exactly the right time, which is immediately after the time of set. It continues the hydration process, helps prevent shrinkage and microcracking, and significantly extends the life of the concrete.
Hi, my name is Mitch Lawrence, and I'm a plant manager here for Ozinga Ready Mix Concrete in Plymouth, Indiana. We're preparing for our third of 5 internal curing pours, so let me show you some of the things that we're doing to get ready. Any aggregate used for internal curing must meet the proper ASTM guidelines. Here at the batching facility, we've created our stockpile in such a way so that it can be uniformly wetted, and we've stored it on a sloped surface so that it can drain properly. We will maintain even moisturization uniformly and continuously over the pile, turning the aggregate as needed to prevent moisture variation.
It is important to note the water inside the lightweight aggregate is not part of the mixed water and does not affect the water-cement ratio. If a steady rain of comparable intensity occurs, turn off the sprinkler system until the rain ceases. At the end of the wetting period, or after a rain event, allow a minimum of 15 hours of drain time. Longer drain times will reduce the surface moisture and improve handling of the fine lightweight aggregate. While draining, the stockpile may be covered with a non-absorbent material, such as plastic. On this job, we are using a fine lightweight aggregate gradation, a number 4x0. An intermediate gradation can also be used effectively. Consult with your local expanded shale, clay, or slate producer for assistance. We are now ready to sample and test the material to determine the aggregate's moisture content or its absorption percentage. This is important to know so we can get the right amount of lightweight aggregate and internal curing water into the mix. So first, we will begin by extracting a sample of the drain material for testing. Here you see a sample of the drain material the technicians will be using for testing. Before the test samples are taken, the pile is turned or mixed a couple of times. The centrifuge test is performed on the pre-wetted lightweight aggregate to determine its saturated surface dry weight and surface moisture. The paper towel method is another way to find the SSD weight. Finding the oven dry weight can be done by cooking the aggregate on a hot plate. We do this to determine the volume of pre-wetted lightweight fine aggregate needed in the mix. A portion of the concrete sand is then replaced with an equal volume of the lightweight sand. After cooking the aggregate down to its oven dry weight, calculations are made to determine the surface moisture and the aggregate's absorption percentage of internal curing water. The surface moisture percentage is given to the batch operator to be used as the lightweight aggregate's moisture correction. The aggregate's absorption percentage is used to help calculate the amount of lightweight aggregate needed to carry a minimum amount of internal curing water in the mix design. The amount of pre-wetted lightweight aggregate needed for internal curing is based on the absorption and desorption of the material being used. For most practical concrete applications, a minimum of 7 pounds of internal curing water per 100 pounds of cementitious material provides an appropriate value for the amount of internal curing water needed for Portland cement concrete. The moisture correction and the amount of lightweight aggregate needed in the mix design is then given to the batchman for mix proportioning.
The only difference between a standard concrete mix and an internal curing mix is that you're taking some of the standard concrete sand and replacing it with an equal portion of the pre-wetted lightweight sand. It's that simple.